Example 7.3. Suppose a radio station operating at a frequency of 60 megahertz has two vertical dipole antennas spaced 10 meters apart, oscillating in phase. The intensity at a distance of 700 meters in the x direction, which corresponds to theta equal to 0, for a single antenna is 20 milliwatts per meter squared. A, what is the mathematical expression for beta and the intensity as a function of theta? B, how many dark and bright fringes are in the interference pattern? What are the angular locations of all bright and dark fringes? And finally, draw a picture of the intensity pattern. C, what is the relative intensity at theta equal to 4 degrees and what is its location in the interference pattern? So a single antenna has intensity I naught, which is 20 milliwatts per meter squared. If there are two antennas that interfere with each other, the intensity at its maximal value is increased by a factor of 4. So in other words, if I look at the intensity of a 2-slit, this is now 4 times the intensity of a single slit or a single source times my cosine squared of beta. So picture-wise, I really have something like this. So if I have something that has that a high of initial intensity, this intensity for 2 sources will then increase by a factor of 4 at its maximal value, where this height change is now 4 times the initial. So to maximize the intensity, it pays to have 2 antennas. So here's what we're going to find here. The 2 antennas that are in phase with each other produce an interference pattern. And we've seen this in the applets. So this is an image from the applet used in lectures. And so this is what we should be looking for, this type of image. We have 2 sources. So we have this guy right here, And we have that one right there. And this is what's producing the interference patterns, these two sources in phase. So now let's look at part A. Oops. Let me try one more time. This is part A. So let's look at this. So the question is, what is the mathematical expression for beta and the intensity function? So the intensity function reads like this. The intensity function is I of two sources is then going to equal to 4 times the intensity of a single source times cosine squared of pi d over lambda times sine of theta. And then I'm going to define this as I max times cosine square of beta. So we need to calculate I max and beta as a function of theta. So the first one that I'll look at is I'll look at the maximum intensity. The maximum intensity is I max, and this is 4 times the intensity of a single source. And this guy, and they told us that this was already 20 milliwatts per meter squared. So then I'm getting 80 milliwatts per meter squared for IMAX. So I now know what this maximum intensity is. The other piece of the puzzle is beta. So now I'm going to look at beta. So the beta phase factor requires us to calculate the wavelength lambda. So we got to do that in order to calculate beta. So radio waves emitted by the antenna travel at the speed of light, which is c. So then using v equals to c, which is lambda times the frequency, that allows me to solve for lambda, which is now equal to c divided by the frequency. Now, they tell us that the frequency is 60 megahertz, so this will be 60 times 10 to the 6 hertz, whereas the speed of light is 3 times 10 to the 8 meters per second. And if I compute this, I get a value of 5 meters for the wavelength. So now that I have the wavelength, I could now calculate beta. So using the given source separation, which is D, and they tell us that it's 10 meters, the beta phase is then going to be beta equal to pi d lambda sine of theta. Now remember, we don't calculate pi at all. So I have d over lambda, which is the interference parameter. So that's got to be 10 divided by 5 times sine of theta times pi. So you could see here that I'm isolating the pi here. So then this equals 2 sine theta times pi, and this is my beta function right here. So once again, I said it, but I'm going to write it right in here. Remember, do not calculate pi unless you are computing the intensity. We need that pi for identifications. So now I can write down my intensity function. I have all the details. So then the intensity function is I of the two sources is then going to be I max times cosine square of beta, which then reads 80 milliwatts per meter squared times cosine of 2 sine theta pi. And this is our intensity for the two sources. So now that we have that, we can go to the next piece. And there's a series of questions that we're asking here. In B here, we're asking the number of bright and dark fringes. What are the angular locations of all the bright and dark fringes? And then draw a picture of the situation. So here we go. To determine the interference pattern, one has to calculate the number of dark and bright fringes. Now, following our discussion from lecture, the interference parameter is very useful to understand the pattern. For example, look at what the interference pattern tells us. So it tells us that d over lambda, which is 10 meters divided by 5 meters, is exactly 2. The fact that this number being an integer tells us that the last fringe ends with a bright. So we know it has to be a bright. And I'm not going to go into other details, but it actually gives you the M value too. But I'll talk about that when we get to diffraction, because I want to follow the same pattern that we've been following. So let's look at that. So now what we're going to do here is that we're going to go look at the number of dark fringes. So we want to look at the number of dark fringes. So we start with the path difference equation. So starting with the path difference equations, for destructive interference, the sine theta function reads sine of theta is equal to lambda over d times md plus 1/2. So now we follow the sequence of m values. So now follow the sequence of m values until sine of theta is greater than 1, and it stops. So remember, m is 0, plus or minus 1, plus or minus 2, etc. So let's look at this sequence here. So if I look at the sequence, it's going to be sine of theta. In this case, the diffraction parameters is 2, so this guy's going to be 1/2. So this is going to be plus or minus, and it's going to be md plus 1/2, but I'm going to write this as 0.5, and then this is 2 here. So now let's look at the sequence. So I start off with 0, so I'm going to get plus or minus, and then I'm going to have 0 plus 0.5 divided by 2. That is less than 1. So then I continue, right? So then if I continue here, then this next one here is going to again be plus or minus 1. And it's going to be plus 0.5 divided by 2. And then this guy's then going to be 1. So let's start summing these values. So you're seeing here that this guy really reads 0.5 divided by 2. That's less than 1. This one's reading 1.5 divided by 2. That's less than 1. So when I go to the next one, I get to 2. And you could see here that now I get 2.5 divided by 2. And that one, this value here, what does it do? It exceeds sine of theta greater to 1. Therefore, this value does not exist. So you could see that I went all the way to MD. MD equal to 1. That's what that is telling me. So now I could then use our relationship from lecture. The number of dark fringes is then going to be, it's going to be 2 plus 2MD. Now remember, what's the 0 for? There are 2 zeros here, right? So there are 2 zeros. And then the fact here is that when you look at this guy right here, we have plus and minus signs for MD. So I need two of these values. So then this becomes 2 plus 2 times 1. So then I see that I'm going to have 4 dark fringes. So I know I have more dark fringes. Now, once again, why was it useful to have this diffraction parameter? Because I know that the final fringe has to be bright. So as a check, that means I have to have more bright fringes than dark fringes. Okay, that's the interference parameter telling me. Now, let's do the same thing for the bright fringes. So the number of bright fringes is I'm going to follow the same pattern, right? So I'm going to follow the same process used with dark fringes, except the path difference is slightly different. So then I'm going to have that the sine of theta, this is now going to be lambda over d times mc, which then means that this guy is going to be mc divided by 2. So now if I follow the sequence, now remember, MC also has the same values as MD. In fact, they're the same parameter. So now I'm going to enter the sequence here. So now I'm going to have 0. So I'm going to have 0. Then I'm going to go to 1. Then I'm going to go to 2. And then I'm going to go 3. And I just keep going. So then I have in constructive interference, there's a central maximum. So there's no plus or minus. That was not true for destructive interference because they're not at the center. So then if I continue, this is going to be, look at that, that's going to be 1 over 2. 2 over 2, that's 1. I already know that this has to stop already, but I'm going to keep going. And you can see here that when I get to 3 over 2, that's 1.5. So this guy immediately tells us that it exceeds sine of theta greater than 1. So then this tells me here that then the maximum value of C is actually 2. So now I could say exactly the same thing as we did before. The number of bright fringes is then going to be, it's 1 plus 2mc. Now, when I look at this thing, what do I see here? Again, what is the 2 for? Because I have plus and minus. But there's a central max here. And in this guy, we have 1 central. That's where that 1 is coming from. So now if I plug in my value, I'm going to get 1 plus 2 times 2. This now gives me 5 bright fringes. And as already stated, we had to have more brights than darks because the interference pattern ended in an integer, which means that it ends at 90 degrees like that. So now let's go look at the interference pattern. So the interference pattern is now known. And we're going to draw this out here. So let's see if I can do a good job. So if I look at this thing, I'm going to say that there's my line. Now I'm going to look for the center line, and I'm going to say that this is my center line right here. And this, so if I look at this thing, what I'm going to do here is that I'm going to start drawing this, but I'm going to draw it off to the side, and then I'm going to copy it. So I know I have to have 5 bright fringes. So let's draw that out. So I'm going to say that here, let's do this like 2.5. Let's say that this is my 1 fringe right here. Now I'm going to start copying it. So if I copy it, okay, then I'm going to insert it now. So here's my, I'm going to center that. And then I'm going to paste 2 more. So there's 3 right there. But I know that at 90 degrees, I have to have a bright fringe. So then I'm going to come in by hand and I'm going to say, but then it comes up and at 90 degrees, it has to be bright. At 90 degrees, it has to be bright. So then I'm going to come in here and I'm going to say, okay, here's where my 90 degrees is at. Right? Here's where my 90 degrees is at. So that's the end of my interference pattern. Now to make sure that we label everything nice and clean, look what I'll do here. I'm going to define my beta, and then I'm going to go through the beta factor. Right? Actually, I'm not going to do beta. Let's look at, so this is the intensity profile. Following the same thing, now let's look at the interference. So if I look at the interference pattern, it's going to look something like this. And then I have my darks. So because these are drawn by hand, they're not symmetric, but that's okay. And then here's my pattern now. Here's my brights. So now, if I look at my beta factor, you could see here that this guy has to be 0, and then at increments of pi, I have constructive interference. And this guy is going to be minus pi, and this will be minus 2 pi. Now, when I look at my darks, it's wherever where the cosine goes to 0. So it has to be odd multiples of pi over 2. So there is my intensity pattern right there. So now if I come over and look at the next piece here, what is the relative intensity at 4 degrees? And what is its location? And where is it located at in the interference pattern? So to determine the location of theta equal to 4 degrees, we must calculate beta at theta equal to 4 degrees. So let's look at that. So I have beta, and this is going to be pi d lambda sine of theta, and we already computed this thing. We already saw that this was 2 sine of theta times pi. Now you gotta be careful here. So there's a couple of things that you really want to pay attention to. This has units of radians. I mean, you can keep sine of theta in radians, but that's not the way the question is being asked. So this here is in degrees. You have to change your calculator setting, or you keep everything in radians, to make it easy, I guess. So now I'm going to put in my values here, and this guy then reads that this is going to be 2 times the sine of 4 degrees times pi. Now remember, do not calculate this in beta form. So when I compute this whole thing here, I get 0.14 pi, which is that is my beta function right here. So now I'm going to go to the intensity pattern. So look what I'm going to do here. I'm going to copy this guy. Let's see how this comes out. To try to expedite my process here, I'm going to go to the intensity plot. So I'm going to go to the intensity profile, and this is what I read. So what I'm going to do here is that I'm going to modify it. In fact, I'm going to make this bigger so it's easier to actually look at. And I'm going to modify this thing. So one, here's what we know. I'm going to look at this guy, and I'm going to put my a horizontal axis. I'm only drawing half of this. I really don't need to look at the one on the right here. Okay? I really don't need to look at this one at all. So what do I know? This guy is I of beta. And I know that this point here is 0, and I know that this point here is 0.5 pi. You see, I'm going from 0, and then I have pi over 2. Now, when I look at the peak of this guy, which a lot of the times I don't really care about, I know that the peak here, this is I max. I max, we already saw, was 80 milliwatts per meter squared. But here's our beta factor. But you can see here that our beta factor that we calculated is 0.14 pi. So that means here is that this guy is going to be high up, close to that. It's going to be almost a third of this thing. Let's say that that's the location here. So then I'm going to bring this all the way down here, and this is the location of beta equal to 0.14 pi. So I know, so what I can say here is that theta equal to 4 degrees is inside the central bright fringe. And is closer to a max than a min. Right? It's closer to the bright fringe, the maximum brightness, and it's not close to over here. So now, what we typically do here is that we calculate the relative intensity. So the relative intensity is that I relative of theta equal to 4 degrees then is equal to cosine squared of beta, which also is cosine squared of 0.14 pi. Now I calculate this, but remember, this has to be in radians, right? It has to be in radians. So when I compute this, I get 0.82, or we could say that it's 82% of I max. This is what the relative intensity is. Now, if we wanted to calculate this numerically, how would we do it? So the actual intensity is then going to be I of the two sources at theta equals to 4 degrees, but then this is I max cosine squared of beta. But we already know what that is. We should just put in the value 0.14 pi. So then this means here that this has to be 80 milliwatts per meter squared times 0.82. And if you compute that number, you get 64 milliwatts per meter squared. And that's going to be the intensity at theta equal to 4 degrees.